All right, so let's continue with the second part of the lecture and finish our discussion of implication graphs and how we're going to use them. But let me first deal with some clarification based on what people wrote here. I think I have a couple of questions that indicate maybe some ambiguity about how we may get the conflict set from a cut. So let me mark something here. If you look at this particular cut, and how did I decide that that cut leads to this particular conflict set, right? And similarly for this, because people are asking, like, for this cut, why is X not there? Well, look, what did I cut? So look at these guys. The cut here is that if I really chop this off, I've separated these guys. Now, each one of these lines is coming from a variable setting, right? So this is a true. This is a true as well. This is a true. And this last guy here is X true. That's why I got these guys here. Let's look at this cut here and see what are the variable settings that are involved, right? So if you look here, this is A, similarly A, and then this is Y, this is Y. This is why we have these guys here. So X is not involved in this particular case, all right? And if you look at this last guy, here are the cuts. Okay, let's look at the variables that are pointing. So A, okay, and then here's Z, and then this is Y. So basically you want to track these guys, the edges that crosses that cut, and see what is on the tail of those edges. And that defines the set of variables. I think this should answer a couple of questions there. Another question was, or observation was, if we look at this guy here, this cut, we get this conflict set. And if we negate it, we get a clause, and that happens to be just clause 7. Yes, so this was a trivial cut in a sense. The clause that it leads to is already in the knowledge base. That's fine. Now, we're going to focus on, if we look at these conflict sets, and now we look at the clauses that gets learned or that correspond to these. As we mentioned, we do have not A, not X, and then the other one is not A, not Y, and the third one is not A, not Y, not Z. Okay, now we're gonna actually define two important notions now. One of them is the notion of an asserting clause. So the key here is asserting. And this is a labeling of clauses that are actually constructed in this particular fashion. And the definition of an asserting clause is that a clause that basically includes only one variable setting at the last decision level. So if we look at these clauses and we look at the levels, so this guy here corresponds to a variable setting at 0, right? And this is at 3. If we look at this similarly, 0 and 3. If we look at this, 0, 3, and 3. So I will say that a clause or one of these length clauses is asserting if it includes only one variable setting at the last decision level. So given that definition, let's call these guys 1, 2, and 3. Maybe we should, yeah, that's fine. These are the numbers of these clauses. Okay, it's bad to conflict with the other guys. We'll find that in this particular case, this is asserting because it only has one guy at level 3. And this is also asserting. And this is not asserting, right? So now we will insist on using asserting clauses when we actually learn clauses, and you'll see in just a little bit why. So now we have the notion of asserting, and now we can distinguish between these clauses, and later we're going to distinguish even more. And then the other concept is the notion of an assertion level, right? So we have an asserting clause, and then for an asserting clause, we talk about the assertion level. And what this guy is basically the second highest level in the clause, right? So you tell me, what would be the assertion level for this particular clause, right? The last assertion level is 3, 0. Very good. So the assertion level, if I want to say that, this would be 0, and the assertion level here also would be 0, and similarly for the other guy. Okay. Now, here's the final observation, and then we will actually be able to put things together and show you how a modern SAT solver works. So the idea is, fine, I'm here, I discovered the contradiction according to unit resolution. What do I do now? Well, I have my implication graph, and this implication graph, I can use it to identify some complex sets and therefore some learned clauses. And what we're going to do is, or at least that's what modern SAT solvers do, they will find an asserting clause. And in this case, we have two candidates. It could be either this or that. And then what they will do is they will go and backtrack to the assertion level. Let's say we picked up this particular clause, okay? And that's the assertion level. What they will do is they will go and say, okay, I'm gonna now backtrack to the assertion level. So I'm gonna undo X, I'm gonna undo C, I'm gonna undo B, and I'm now at level basically 0. And then they will add that clause, okay? And then they resume their work. So they did two things here. They did non-chronological backtracking. They didn't just go back and try the other value of X or the other value for C or B. They just went to earlier level and they added a clause. So they did close learning. So non-chronological backtracking and close learning, and they're tied. Now, the story gets a little bit more interesting when we see the code, because this dramatically changed things beyond what you may be imagining now. And it took even the community a little bit to actually realize this. But the key concepts here again is, before we move on, because we're going to see them again, is the asserting clause and the assertion level. Shortly, someone may be asking, why asserting clause? Because asserting clauses end up being empowering. Not every learned clause in general is empowering, but assertion clauses are empowering, and they play an important role. So let's go ahead now and put everything together. And the way we're going to do it is I'm going to show you the code for a modern SAT solver based on these concepts, and then we're going to do a full trace of an example up to the point so that you can see how things all come together. And then what we're going to do is we're going to make a number of observations about this class of SAT solvers. One of them is, no, this is no longer DPLL with some improvements. In fact, it's technically incorrect to call it DPLL in a very specific way that we're going to go over. So let me pull the code for a modern SAT solver, and then where we put all of these things together, and then we will see how it works. All right, folks, let's look at this guy. And okay, it looks scary, but let's walk through it basically line by line, and then we will do a full-fledged example that will make things very clear. Here's what we're doing. We're going to call this, we're going to call this DPLL plus, okay? A misnomer, but fine. And delta is our knowledge base. And in this case, we're simply going to return true or false, depending on whether that's satisfiable or not. Okay. What we have here is D, which is our decision sequence, right? These are the decisions that we're making, okay? They're going to be a list. And then we have gamma, which is these clauses that we're learning. And initially that's empty, right? So we haven't learned anything. And then there's a loop that says while. It keeps repeating. It starts by running unit resolution. And then it says, but look what unit resolution is applied to now. It's applied to three things: the original knowledge base, the learned clauses, and the decisions. The decisions here, you can think of them as unit clauses. So if I say, let's try A equals true and B equals false, right? These are unit clauses. So the decisions together with the learned clauses, together with the original clauses, that's what I do unit resolution on. Now, so we have two cases here. The case where unit resolution finds a contradiction and the case where it does not. Now, if unit resolution detects a contradiction, that's this case, then, well, first we have to see, were there any decisions here? If no decisions, what does that mean? That means the contradiction was found based on the original knowledge base and the learned ones. What does that mean? That means my original knowledge base is inconsistent. I declare failure. Okay, so this is if the contradiction was found without me having made any assumptions. Okay, otherwise, this is what we talked about. I'm going to do the implication graph thing. I'm going to find the asserting clause. I'm going to find the assertion level of the clause. And then I'm going to go ahead and erase um, decisions that are after the assertion level. Okay. And so this is now going to be shortened. I had a bunch of decisions. I erased some of them. I'm doing backtracking. And then I'm going to add the clause that I've learned to the set of learned clauses. Okay. That's what we just talked about. And then the process repeats again. Otherwise, if there is no conflict that unit resolution did not detect a contradiction, what do? I just make another decision. Okay, so I try to find a literal that is neither, implied or its negation is implied, and then I will add it. So I just made another decision and just repeat. Okay, we have to see a concrete example, and then you'll see how now this looks very different from, for example, depth first search, right? But let's just tell you, you are making decisions, and then when you get a conflict, you do this implication graph thing, you find a learned clause, you find an assertion level, you erase enough of your decision, add that clause, and just repeat the process. So let's take a concrete example. All right, folks, so this is the example that we started with, and now we're going to trace this algorithm. So initially, what we will do is we will start with an empty decision sequence and then an empty set of learned clauses. And then we start making decisions. But we're going to assume that initially we went and made this decision that is A equals true. Now, if you go run unit resolution, in this case, you will not find a contradiction. So we're going to go make the next decision. And let's say B equals true. Similarly, you will not find a contradiction using unit resolution. And then let's say we make the decision C equals true. Again, no contradiction. And then we make the decision X equals true. So this is basically is emulating what we tried initially using depth first search. But and remember, this was the level 0, level 1, level 2, level 3. All right, these are the levels. So the first decision was made at level 0, level 1, level 2, level 3. At this point, what happens is unit resolution discovers a contradiction. And we've seen that before. We've seen the implication graph for that. And we saw that that implication graph leads to two types of asserting clauses. One of them is not A, not X, and the other one is not A, not Y. So both of these were asserting. This was at level 0, 0, 3, 0, 3. Assertion level here was 0, remember? And similarly, assertion level here was 0. So we're going to pick this guy. Okay, we could have picked the other one as well, but we're going to pick this particular guy. So what does that mean? Let's look at the code. So our alpha, if we're going to write it here, so we're here, right? Unit resolution detected a contradiction between this guy and delta. This guy is empty. Okay, so what is this guy? The asserting clause, that is not A, not X. Okay, now we need the assertion level. What's the assertion level? In this case, 0, right? Okay, then after that, what this guy says, D should be modified. It should be the first M plus 1 decisions in D. So M is 0, so the first decision in D, so that is basically A equals true. What does that mean? I'm erasing these decisions. Right? So I'm really backtracking all the way to level 0, right? I'm removing these guys. So this is where I am now. And then it says add close alpha 2. So this gamma end up being basically now has, and now my knowledge base is the original delta plus now this gamma, okay? And now what do? I'm done with this. I just repeat. So I go back to the top of the loop. What does the top of the loop says? Run unit resolution now. Okay, so the difference now is when I initially ran unit resolution, I was running on the original knowledge base. Now I'm running unit resolution on what? Okay, so now we're basically second iteration. So this was first iteration, and now basically here, if second iteration of this loop. The difference now is I'm doing unit resolution on the original knowledge base on this modified gamma, which now has this clause, and on the decision sequence that contains A equals true. Okay, all right. So now what's going to happen? Unit resolution will actually find a contradiction. And I'm actually going to draw the implication graph for you in this particular case. Let me do it here. It's going to be a little bit smaller than the other ones we looked at. Let me do it here in blue, and it's going to be this implication graph. So we're calling that clause that we added number 8. Okay, so we're going to call this, we're going to put it here as 8. That is not A, not X. Okay, and if we're going to do the levels in this case, this is level 0. And basically everything here was derived at level 0. So this is level 0, this is level 0, and this is level 0, and so on. Okay, this is our implication graph. This is how we got a contradiction in this particular case. Because A is true, and with this new clause that we have, I derive that X is false, and then using clause 4, I end up deriving that Z is true, and now using clause 6, I end up getting the empty clause, and I do have a contradiction. So now what I need to do is repeat the same process, right? I need to find an asserting clause, ... So let's look at the cuts in this particular case, and the asserting clause, you know, this cut here, leads to a conflict set that only has a single setting, A equals true. So from this cut, I actually learn clause not A. So I basically learned a unit clause in this particular case based on this implication graph. Now, what is the level here is 0. And is this an asserting clause? Yes, it is an asserting clause, because an asserting clause should have one variable setting at the last decision level. So that is true. The technicality here is, if I want to go and run this, I need to know what is the assertion level. And the assertion level in general, we said it would be the second highest. Now, when you have a unit clause, there is no second highest. So by definition, the assertion level is -1, and you'll see it works nicely with the code. That's basically the thing. So let's keep going with this. So what happens here? Now that we have this, our alpha is the unit clause, not A. Our assertion level is -1. Let's see what happens to the decision sequence. So we need to get the first, so -1 + 1, 0. First 0 decisions, so that means this guy is empty. So I'm erasing the decision A equals true. And now my augmented guy here will end up being this guy, not X, and not A. Okay, this is what happens in this case. And then I finished this iteration, and now I go back and execute the third iteration. What happened here is I learned effectively that A must be false, right? Because I learned this unit clause. So you'll have to continue with this example. Let's make a couple of observations on this. The first one would be that we will make a further distinction between asserting clauses so that we pick one. And then we will make a couple of observations with examples on the behavior of this algorithm to see how much it deviated from DPLL or depth first search. If you take DPLL to mean depth first search, then as I said, you will see that this is no longer depth first search, not even an improved version of this. And therefore saying that this is DPLL and therefore depth first search is technically incorrect. So let's first do the one observation, and this you need for your homework, about how to even select from among asserting clauses. Okay, there's a question about how did you get assertion level -1? Is it because the asserting clause is only unit? Yes, because by definition, the assertion level is the second highest. So if you have a unit clause, there is no second highest. So by convention, we say -1. And again, it works okay with the code. So M is -1, correct. Okay, so the idea was I'm gonna have yet another criteria for picking not just any asserting clause, but one particular type. This is something that people came up with and it worked better. I have to say that most of these advancements that we talked about came up with a set solver known as ZShaft from Princeton, which was really a turning point in how things happened with regards to set solver. So what we're going to do is we're going to take a look at the same example we looked at before as far as the implication graph. And then we had there two asserting clauses, and we're going to see how we're going to pick one of them based on this criteria that people have identified and found to be useful. As I mentioned, these are example of heuristics or ideas that turned out to be quite influential. People can find other ones. Some of the things we talked about are theoretically justified, like this notion of an asserting clause being empowering, and some of them are just heuristic, like what we're going to talk about. So this is exemplary of something that made sense, but people could have, discovered more or other things that perhaps work better. So let's go back to this example here. And this is what we had. Those are our decisions, and we had two implications and then a contradiction, and you can see levels 0, 1, 2, 3, and these guys were all derived at the latest decision level, and these are the names or the numbers of the clauses that participated in doing these derivations. And I have 3 and 3. Okay, so what we're going to define is this notion of a UIP, which is what people call unique implication point, right? And the unique implication point, it is a variable setting at the highest decision level, which lies on every path from the latest decision to the contradiction. This is the contradiction. This is the latest decision level. So you need to find a variable setting that I must go through if I were to go from this to that, right? So I can go from this to that this way. I can go that way. That's basically it. The two candidates here for UIP are, what are the candidates for UIP, right? So I'm looking at a variable setting at the last decision level. So it's this, or that, okay? And which one of these three is a UIP? Is this a UIP? Is this a UIP? Again, it's a variable setting at the highest level, which lies on every path from the latest decision to the contradiction. So this is basically, in a trivial way, is a UIP, okay? How about this guy? Is this a UIP? If I go from this to that, do I have to pass through this? And people are saying yes. So this is a UIP as well, okay? So this is UIP, and this is a UIP. What about this guy? Z equals true. Is this a UIP? No, I don't have to go through it, right? I can go this way. So basically we have two UIPs in this case. And then there is the notion of a first UIP, which is UIP closest to contradiction. So this would be this guy. That would be basically the first UIP. All right. So the first UIP, again, is the one that is closest to the contradiction. And the idea now is that when I do basically choose an asserting clause, I want to use one that actually includes the first UIP. So if you remember, in this particular case, we had two cuts. There was this cut, and then there was this cut. And the first cut actually gave us the clause not A, not X. And the second cut gave us not A, not Y. Both of these were asserting, but if I want to use the first UIP asserting clause, I will use actually this one instead. Again, people found that this first UIP asserting clause is something that you want to choose. This is an example of a heuristic, and here's the basically definitions in this particular case. We need to make two more observations on this algorithm. Maybe we'll do one with an example and just hint at the other. And this is important because this example I'm going to show you next will show you to what extent this algorithm now deviates from depth first search, right? Which is what people understand DPLL to be. And the point behind this example is you'll see that this algorithm now, which we got to by making improvements to depth first search, is no longer doing depth first search. In fact, it doesn't have any memory of where it's been. So before I show you the example, let me just stress something. What does depth first search do? Depth first search takes a variable and say, let me try this, let me try that. Let's say true, false. And let me take another variable, let's say B, and then let me try false, let me try true. Now, when you extend this search tree, if you see the search tree, every branch in the search tree corresponds to a distinct variable instantiation. So if you look at the bottom or the leaves, they correspond to all possible variable instantiations. And the algorithm is complete because it makes sure that eventually it checks them all. It's not going to miss any. And it does not check any of them multiple times because each one of these is distinct. So if it goes down here to check this guy, and then it goes backtrack, checks another distinct guy. So in a sense, it has a memory of where it's been, and it will not go to a certain place multiple times. And it makes sure that it's going to visit every place. We're going to see in this next example how this algorithm that now we're calling DPLL plus, or we're calling it a modern set solvers, behave quite differently than that. And it gets its completeness not by remembering where it's been and avoiding going to the same places, but from something else. So we'll end with this example and perhaps another observation. So here are this example, these 6 clauses. I have A, B. Okay, so this is our knowledge base. And by the way, before I forget, let me mention that it took a while for people to understand really what's going on with these modern set solvers. If you want to get a more detailed treatment, there's the Handbook of Satisfiability, which is a very thick volume. And the paper on these modern set solvers was written by Nat Pipastrawat and myself. Nat was a PhD student here, and he actually did a lot of fundamental work on set solvers and understanding them, including introducing the notion of empowering clauses. So you can consult that. But let's go to this example. So here's what we have. And let's say we're running this modern set solvers, and we decide initially to go ahead and try A equals false. So this is our decision sequence, right? This is the first decision that we made. Now, if you run unit resolution now on this knowledge base and that particular variable setting or that unit clause, which is not A, you will get a contradiction. And the implication graph will look like this. So let me do it, because then we're going to see what kind of clauses we are going to get. So you're going to get C equals true, D equals true, and let me make this guy equals true, and then we're gonna get, and finally the conflict. Okay, so here's how it looks, and let me put the numbers on these. So this would be 1, 2, 3, and 5. Nope. So 2, 3, these would be 4, 4, and this would be 5, and this would be 6, 6. Okay, that's what happened in this case. The very first decision that I made at level 0, A equals false, basically led to a contradiction, okay? And if you look at the cuts in this particular case, here's one cut, and here's another, and this is one more. There's more, but if we look at these guys, these are the ones that would lead to asserting clauses, all right? And what this guy would lead to is the asserting clause A, and this would lead to the asserting clause not B, and this would lead to the asserting clause not E. These are the ones. So these are the 3 asserting clauses. And this guy would be the first UIP. So I'm going to go ahead and basically do that, and which basically means that I will go ahead and erase this decision. So here's -1, the assertion level. I'm going to erase this guy and therefore go to the decision sequence, the empty one, and I'm going to add this not E to the knowledge base or to the set of learned clauses, and I'm going to basically repeat, go to another iteration. So that's what happened in this particular case. Now, the next thing that's basically going to happen is that now unity resolution will not detect a contradiction. And when I go ahead and pick another decision to make, neither the variable A nor its negation is implied. So I could have picked A, not A again. In the second iteration, I may have picked again to do A equals false. All right? There is no depth first search tree anymore. A decision sequence could be repeated in this particular context, and that's impossible to happen when you're doing depth first search. Now, if you think about it, then you may say, oh, wait a minute, what's going on here? If I may repeat certain decision sequences, would I get in an infinite loop? In general, yes, and that would be a problem, and that would make your algorithm not complete. But if you see what's going on here is, the algorithm is doing some kind of a combination between search and inference. So you can think of the decision sequences are being guessed. Let's say heuristics effectively are like guessing, right? So I'm guessing some decisions. Now, two things are going to happen. Either my guesses work and I end up satisfying the formula and I'm done. Now, if my guesses are not working, what does that mean? As I'm making more decisions, I'm going to hit a contradiction which says, oh, your guesses are bad so far. But look, every time there is a failure, there is a contradiction, what happens? What happens is clause is learned, and that clause makes unit resolution even more powerful. So every failure is turned into an opportunity to do what? To make unit resolution more complete. So it's an interesting game. It's like, I'm guessing, but your guesses are not going astray. If they don't work, they help us. So either your guess works and you solve the problem, and if your guess does not work, it's an opportunity to make unit resolution more empowered and more complete. And yes, as someone said, by growing the gamma, and gamma gets more clauses. So the guarantee for completeness is because in every failure, you are incrementing or improving the completeness of unit resolution, which is a completely different story than depth first search, where you get completeness by making sure that is you have a depth first tree and you're traversing it systematically, so you don't go to places multiple times, and that you eventually go to every place that you have to go through, and so on. Again, you can if you want to get all of the theory behind this, you'll have to go into the notion of empowered clauses more formally and so on, but this is all we want to do here. Let me say there's one more example. Okay, and your text, immediately after this, there is basically an example showing you why asserting clauses are necessary. That if you really do not learn those kind of clauses which are empowering, you get in trouble and you can get into an infinite loop. All right. So what's guaranteeing the completeness here is the learning and the learning of particular clauses. Okay, this is all I wanted to say. I'm done here, and thank you. I will see you on Thursday.